So what is it we are trying to prove? So I told you about constructing this cohomological field theory for the Hilbert, right? The higher genus cohomological field, or better to say cohomological field theory associated to higher genus Gromov-Witten theory of Hilbert C2. Okay, so so where were we left? So I talked about this quantum differential equation that the R matrix satisfies. Yes. And the flat coordinates. So I just continued the last discussion. So two main properties to construct cohomological field theory on Gromov-Witten theory of Hilbert C2. Of course, I mean, you construct the R matrix, and then the coefficients of the R matrix are given by your Gromov-Witten the invariance. And so there are two properties we are going to use. One, that there exists a unique R matrix, which we discussed last time. It's a semi-simple cohomological field theory given to Al-Telemann, tells you that there is such unique thing associated to this vector space that we started with, the A algebra, and the R algebra is going to be some power series algebra in formal variable Q with coefficients and equivariant parameters T1 plus T2. Together with the quantum product, the big quantum product, and then non-degenerate pairing on V with coefficients in A, we discussed this last time, which generates T equivariant Gromov-Witten theory of Hilbert of C2 in all higher genus. So this is one property, and the other one is that two R matrices, this is something that you can investigate, but I'm not going to prove it. Two R matrices associated to this thing. Actually, yeah, I'm going to prove it. And this one I forgot. I'm going to prove it. With coefficients in this power series must differ by this term. It's basically right multiplication by this term, exponential of sum from j equal to 1 to infinity a 2j minus 1 z to the 2j minus 1, where these guys are diagonal matrices with coefficients in A, with entries or coefficients in A. So maybe I say this here. This is a statement of given tall Telemann classification of semi-simple cohomological field theories. I mean, applied to T-equivariant Gromov-Witten theory of Hilbert of C2. Right? Okay, good. So this is the two properties. So what was the theorem that we wanted to prove? So I guess I called it theorem 1 or something. So here's the theorem we want to prove. So I mentioned it last time, but I write it again. So theorem 1 is about Gromov-Witten theory of Hilbert of C2. You see, all of this business, all of this semester, we have been talking about correspondences between different Gromov-Witten theories. The quantum cohomology is captured by Gromov-Witten theory. In this point of view, captured by a certain cohomological field theory associated to a Gromov-Witten theory, right? And this Gromov-Witten theory of Hilbert of C2, this is your targeted space. And then when we relate it to threefold theories, that's also the Gromov-Witten theory of a threefold, right? And also on the DT side. So we have the DT theory of the threefold. So the R matrix, this is the theorem, the R matrix of the T-equivariant Gromov-Witten theory of Hilbert C2 is uniquely determined from the T-equivariant covariant genus zero theory So all higher genus invariants can be determined by genus zero invariance. And the Divisor equation, the Divisor equation and degree zero invariance. Degree zero invariance. Okay. And in fact, we have higher genus invariants, and those are the following way. So the only non-trivial, non-vanishing higher genus invariants are the following ones. So if I give you a basis of cohomology theory of Hilbert of C2, those are given by partitioning n however you want. So you have mu1, mu2, mu_r the way you want. So you have some mu like that, some n-point function or r-point function, and you're looking at genus 1 stable maps, 0 mark points, so only mu. And this is given by summing over all partitions of n, mu restricted to eta, integral over M11 of the Euler class of the rank 1 Hodge bundle, the dual of rank 1 Hodge bundle tensor with tangent at eta of Hilbert C2. It's tangent bundle. divided by Euler class of tangent at eta of the Hilbert of C2. So this is the invariant that you will get this way. And for higher genus, this is going to be equal to, again, summing over all torus fixed points. And these are the torus fixed points of the Hilbert of C2. These are given by Untitled type diagrams. And they're in the focus space where your cohomology theory lives, right? They are given, their image in that space is given by Jack polynomials. So this means restriction of a certain partition into that t fixed point of the Hilbert space, or to that Jack polynomial representing the t fixed point. So this is a localization argument. And this is basically the integral over mg of Euler class of the rank G Hodge bundle divided by so these are the only non-vanishing invariants, and here mu is the Nakajima basis and mu restricted to eta is the restriction to t fixed point. Corresponding to this eta, which can be calculated from the Jack polynomial of eta. Remember that the t fixed points, their cohomology and everything was, we did them in the calculation. We looked at the finite Young tableau diagram, and we looked at the characters. We have x and y's, and x has the t1 character and y has t2 character. So we can precisely write down what is the equivariant character of that configuration. And the Jack polynomial can be written as soon as you write that configuration down. But we had a formula for the Jack polynomial, right? So remark, apart from mu Hilbert C2 and Hilbert C2 genus bigger than 0, bigger than 2, all other invariants vanish. All other degree, those are the degree, by the way, degree 0 invariants vanish. 0 invariants vanish. Okay. Yeah, I made a that was a typo basically. I mentioned this, the degree zero map, not the genus 0. It's a genus 1. Yeah, genus Genus 1 and some number of 1. Yeah. Marked curves which have constant maps, which are being sent to the target variety by constant maps. They're contracted to a point. Okay. Okay. So in order to prove this, basically the divisor equation helps. So let's discuss about divisor equation. So the formal Frobenius manifold, which we discussed before, is defined at the origin along the line minus t times this is state vector, which is v. And we discussed that every Frobenius manifold comes with a potential, and the quantum product is captured by taking the derivatives of the potential and the product of structure. So the potential of Frobenius manifold, or formal Frobenius manifold, is given by F0 Hilbert C2 minus T to 1 minus N2 plus gamma, which has the following description. So what does this mean, I tell you? And this is again following the discussions of the last session. That is equal to summing over d equal to 0 infinity of q to the d, sum over r0 infinity, sum over m equal to 0 infinity, t to the m, gamma factorial, m factorial, gamma, this is the notation, this is what this notation means. So I have some gamma class in here, and I add plus this vector, this is the divisor. This is some multiple of the divisor by the t. This is the tautological divisor of Hilbert. And I put r many of these gammas in here, and I put m many these in here, and I look at basically this partition function. And the divisor equation, we have done this before when we were doing higher genus. Remember that whenever I had some basis of cohomology and I could split it into the divisor classes and non-divisor classes, and the divisor classes appeared as an exponential term in the higher genus Gromov-Witten potential. Remember that, right? So something similar to that happens in here, which is dt, well, this is obvious, basically. So dt r factorial m factorial. And if you don't remember why this was the case, at least in case of a variety, we did this calculation before. This exact formula we did before. similar to this actually, which implies that we get q to the d e to the d times t. You see now you have this divisor class which is equipped with this equivariant parameter, and this is basically saying that the contribution of these divisor classes, when you put m of them over there, appears in an exponential term. So here gamma is in V, and D is minus 2 and minus 2. Okay, so this is the result of calculation. So this is basically by taking advantage of the divisor equation for this particular class. Okay. This particular class, it's a class, but it's also because we know that V has the structure of a Frobenius manifold now. Points of V are given by these cohomological type classes, right? So because what is our V? Our V is basically the Fokker space extended over Q with this equivariant algebra. So this is a point of V. So what we are doing in here is we are using the divisor equation for the point of V next point of V, which is given by this class. Okay, so that's the divisor equation. So what does this imply? Because of this exponential structure, this actually implies that the following. The potential near the point T1 minus 2 in V, n minus 2 in V, is obtained from F0 tail-bend of C2 minus T 2n minus 2 plus gamma, which is really the same as F0 tail-bend of C2, only for the point gamma in V on this Frobenius manifold, restricted to when I replace Q with Q times e to the T. You can see that. This is Q times e to the T to D. That's the beauty of the divisor equation. Now, let omega be the cohomological field theory associated to Gromov-Witten theory of tail-bend C2. The genus 0 data omega is exactly given by the Frobenius manifold at the origin. So we can define some notion of, so basically, the genus zero data of this cohomological field theory, let's call it gamma, and then everything else we can shift by points along this line in the Frobenius manifold, and then recover everything else from the genus zero data. That's where this argument is going. And so in the following way, so we can then define the, let's call it something like minus t times 2n minus 2 shifted cohomological field theory by as follows. So omega of minus t and minus 2 shifted theory of this thing is equal to PMM factorial and rho lower star of omega g n plus m omega, this is R many terms tensor e to the m, which is the same by what R, but by the calculation we did, it's the same as omega gr, R many terms restricted to this specialization. Okay. Okay. So yeah, this is how you can actually, move, basically compute all the other invariants. So now we can discuss the same thing for the R matrix corresponding to the genus zero theory versus the R matrix corresponding to the higher genus theory. So as soon as you realize what the condition is that this R matrix satisfies, then you can determine the whole theory using the coefficients of that R matrix. Let R hill be the unique R matrix associated to omega, the shifted homological field theory is obtained. Is obtained this. Let's do it this way. I want to say it is obtained from genus zero data F0 Hilbert C2 minus T 1 n minus 2 plus gamma ga by the unique R matrix which is this guy also shifted by this point. So minus T plus gamma, which is the same as the R matrix for the genus zero data restricted to Q e to the T. This is by the uniqueness of the given Tal-Telemon classification. So if you have certain R matrix, and this property of the R matrix we have realized by basically writing down the divisor equation. We have a cohomological field theory. We want to make a statement about what is this R matrix. We know that the coefficients of R matrix are given by the genus 0. For the original cohomological field theory is given by genus 0 data. Then we realize what does this shift do to the Cohomology potential. It does this to your generating series. And hence, we have a unique R matrix again with needs to associate to the shifted cohomological field theory. That cohomological field theory. Which by definition actually is the higher genus cohomological field theory. Okay? So as soon as you realize that this condition is satisfied, this is what you need to have. You look at this R matrix and this R matrix satisfies a certain quantum differential equation. So plug in this change of variable into it and just see what is the differential equation that must be satisfied. So this implies that basically this differential equation must be satisfied. d dt of R help must be equal to Q times d dq of R help. Okay? So now we can basically use the second property I mentioned to you. So the two properties of this R matrix, the one was that it is a unique matrix. Second one was that if you have two R matrices, then they are related to each other by certain terms with coefficients in your algebra. So that you can investigate in here. So proposition the R matrices associated to this Frobenius manifold, which both satisfy this differential equation, must differ by right multiplication by exponential of a2j minus 1 z2j minus 1. Okay? What is the point? The point is that you would like to compute this cohomological field theory by computing this R matrix. And then you realize that whatever matrix it needs to satisfy this differential equation. And then you might have multiple solutions to a differential equation. If you have two solutions to this differential equation, there must be different by multiplication by these terms. And then you can actually investigate that these terms do not have any dependence on Q, on your formal parameter Q. So that basically just tells you that you can associate a unique R matrix in here modulo this terms independent of Q that determines this cohomological field theory. Okay, so I'm not going to go to prove this. But here it is. So, conclusion. is the following. R Hilb is the unique matrix which satisfies minus d dt R Hilb equal to Q d dq R Hilb. And has Q equal to 0 restriction okay, which equals our matrix of the restricted cohomological field theory omega Gn restricted to Q equal to 0. Now, since omega Gn restricted to Q equal to 0 concerns constant maps, of genus G curves to Hilb n of C2, then the cohomological field theory can be written explicitly in terms of Hodge integrals. Okay. In some sense, this is a brave statement, but my feeling is that this is structure and the divisor equation. All of this basically tells you that you have a quantum differential equation with a solution, and the solution of this quantum differential equation at point t is determined by the boundary condition. And the boundary condition is the genus 0 data. So in some sense, the R matrix is the solution of this differential equation with the boundary condition given by R matrix of the genus 0 cohomological field theory. And the rest is somehow deformation of these things along the genus. I mean, just look at the description of the cohomological field theory anyway. For higher genus, the description is literally given by the lower genus one is specialized into Q replaced by Q times e to the t. It's like you're growing it, right? So you're looking at the flow of this differential equation. My feeling is this, but this, yeah, seems like that's what it is. So the moduli space of maps in degree 0, because remember that Q was keeping track of the degree. Now we are looking at degree 0 maps from genus G2. So this is basically given by M bar G R Hilb n of C2, the degree 0 maps That's the same as m bar gr itself times Hilbert of C2. The moduli space matches because all the curves are being contracted to points. So basically this is enough to show that your mu Hilbert C2 is the way that we have in the statement of the theorem. And same thing for okay. So the fact that higher genus theta can be captured from the degree zero maps and the Hodge integrals is by looking at the specialization of your R matrix to Q equal to 0. That just gives you the cohomological field theory of Q equal to 0, which is associated to genus 0 Gromov-Witten potential. And Gromov-Witten invariance in genus 0, when you're looking at, and in degree 0, when you have genus G maps with R mark constant to this, are given by Gromov-Witten invariance given by integrals over this moduli space. And those integrals are, again, exactly the ones that I just described in the statement of this theorem. So this is somehow the sketch of their proof. This is, again, proof of the Pandre-Bande. I mean, it's very involved. I mean, Pandre-Bande and Schenk. Okay. So that is that, and then you have the second theorem, which discusses the following. There exists a triangle, and again, this is just roughly a sketch, but don't go into the detail. There exists a triangle which is big quantum cohomology of Hilbert of C2 is equivalent to Gromov-Witten theory of this map pi C times C2 to m bar Gn. And I will tell you what is that map about C. Donaldson-Thomas theory of pi C times C2 going to m bar Gn. And in fact, there is something also, some other thing which is, it maybe makes it into a diamond, which is somehow the big quantum cohomology of sim n of C2. This is the orbifold Gromov-Witten theory of this space. It's the singular thing, that's singular. This is the resolution of sim n of C2. And you can actually complete this diagram this way. So let me just tell you how do they prove it. In fact, what they prove is the following. It's very involved. So they look at the cohomological field theory associated to Gromov-Witten theory of, this is the universal curve. This C is the universal curve, pointwise over every point of this moduli space. This gives you a curve of genus G and N. Okay? So they look at the cohomological field theory associated to a threefold, a family of threefolds now. This is a family of threefolds. Always a curve times C2. And they look at the R matrix of this thing and the partition function in here. And they manage to match that cohomological field theory with this guy. Cohomological field theory with this target space. Okay? This is on the Gromov-Witten side. Then, on the DT side, in fact, they don't look at sheaves, they look at something called a stable pair. It's a famous thing. It's an invention of Pandripandi and Thomas, a beautiful paper they wrote, the stable pair theory. Some notion of a sheaf theory, DT theory. They matched that cohomological field theory associated to a stable pair moduli space with this guy. So this they match with here. This they match with here. And then they prove that these two things match. That's how they prove it. It's very, very involved. It just turns out that you write down the description of cohomological field theory of this one, it matches with this guy. Algebra structure, inner product structure, all of that. And the one for this one matches with this guy. And then they need to actually prove that these two guys match. That's a lot of work. That's why in the beginning of this last session, or the week before, it was a little bit confusing. Why are we studying Siman of C2 all of a sudden? We want to make a statement about Hilbert of C2. But no, the reason is because we still want to, prove the triangle, but we do it this way. They do it this way. There's really a lot to learn, really, from what these guys are doing. That's quite amazing. So let us just discuss it. Let me discuss the Gromov-Witten theory of C times C2 over M bar Gn. Let M bar Gn be the, let C to M bar Gn be the universal curve. Universal curve with universal sections P1 to PR, which is M bar Gn goes to C, or GR, let's just R many points, R. Okay, associated to markings. Now let pi C times C2 to M bar GR be the universal local curve. When I say local curve, I really mean local curve threefold, because locally looks like a curve. Local curve threefold because this is like C together with an affine space. Local curve threefold over M bar Gn R. Now the torus, as I'm writing this thing, I claim that everything would make sense to you because we did good discussion on this. The torus T acts on C2 and Gromov-Witten and DT theories of pi are defined by pi relative moduli space of the stable maps and stable pairs. So this is basically the part that I said for the dt part. They don't really match the dt partition function, but they match it with the stable pair partition function. Do you know what the stable pair is? Everyone here knows what the stable pair is. If you have some curve, the stable pairs are the closest honest algebraic objects that can capture, using sheaf theory, basically the compactification of the moduli space of the stable maps. If you look at the ideal sheaf of a curve, as the curve deforms, the ideal sheaf can basically, ideal sheaf of a curve means it's some torsion-free sheaf associated not necessarily to just a curve, pure curve, but it could have zero-dimensional subschemes attached to it. It could have non-reduced structure. So you could have some mark points on the curve, but then your markings, you can realize your markings and non-reduced structures, zero-dimensional subschemes, and under the further deformation of the curve, this zero-dimensional subscheme can move off of the curve. But the stable maps never do that, right? The stable map always has a curve with the marking lying on the curve. It's not like you're marking, well, algebraically, your marking is still a point, but what if your point is moving off the curve? So the stable pair is a mechanism to keep the marking, to keep that point on the curve. So basically that's what it is. So your stable pairs are sheaf theoretic objects modeling a curve with marked points on it, with some divisor on it. So if you have a divisor P on your curve, naturally on your curve it defines a line bundle because it's a divisor. So if I call the C, OC of P would be a line bundle. And it has a section from O of C to here, like that. Now if you would like to realize this in the ambient threefold surface, whatever, you have some map from the structure sheaf of your ambient variety that surjects onto this thing. So you just compose this map and you will get a map, honest map from O of X to the push forward of this line bundle into the ambient variety. So maybe I call the push forward of this line bundle some sheaf F. This is some sheaf that over its own support, in fact, it's locally free. But when you push it forward to the ambient variety, it is just a pure sheaf with pure dimensional support, pure one-dimensional support. So really, if you give this to any algebraist, they would, and you ask them, what is this? They would tell you, well, I'm seeing a sheaf together with a section. This is a pair, a sheaf and a section. And in order to make sure that this divisor lies on the curve and remains on the curve, there's a certain stability condition that you need to associate to this two-term complex in the derived category. So stable pairs are two-term complexes in derived category together with this notion of a stability condition. And they model a curve with a marking on it. Okay? And that's what it is. So when they match the DT theoretic data, because this is, again, some sort of sheaf theory, sheaf with sections, they really mean matching with the stable pair data. The cohomological field theory to the stable pair moduli space, associated to the stable pair moduli space. But okay, so now, for stable maps, we define cohomological field theory lambda tilde via the moduli space of pi relative stable maps to pi relative stable maps to C2 M bar G. you do realize what a complicated moduli space this is, right? We are not just looking at one variety. For as soon as you fix a particular point inside here, you have a threefold. And you can look at the moduli space of a stable maps to that threefold. So the idea is that there is a moduli space that lies on top of this thing, whose fiber over every point of this guy is a moduli space of a stable maps to this particular variety. That's what I will call pi relative moduli space of a stable maps. Okay. Okay, so this is based on, this cohomological field theory is based on this algebra, A tilde, again, some equivariant algebra and the power series in some variable u with coefficients in an equivariant algebra, and some focus space extension by this equivariant algebra. And this Fn is the piece of the focus space whose basis is basically given by partitioning n. But we know that the actual one is the direct and infinite direct sum of cohomology theories of Hilbert. Okay, so we have this, and now here's the remark. The algebra free module algebra A tilde free module V tilde and inner product structure for this lambda tilde are all the same as cohomological field theory defined on orbifold Gromov-Witten theory of sim n of C2. Okay? So this is what it is. So now so when we construct this cohomological field theory, it gives you an edge, the lower edge going to the cohomological field theory of sim n. And the other one, the stable pairs theory, basically matches with the Hilbert, and then these two guys talk via another identification. So let mu1 to mu r, partitionings of n, and let epsilon be a map from this moduli space mh I mu1 mu r to m bar gr be the moduli space of stable maps to fibers of pi. So this is obvious, right? This is the moduli space. For every point of this moduli space, the fiber of pi, pi was this map. Okay, so you have this, and what am I going to say about their proof? So let's see. So maybe this is important, and this kind of gives you an intuition. So how do we realize these stable maps in here? Okay, so the fibers of epsilon. This map. Over a point, let's call this point C together with R mark points. Is the moduli space of stable maps of genus H in my notation to C2 times C relative to divisors determined by the markings of C with boundary condition mu I over the divisor C2 times Pi. Okay, so do we understand what this is? This is something very similar to the story when I was reviewing the Pandripandia-Kunkov proof of quantum cohomology correspondence with Gromov-Witten theory, for instance, on Hilbert of C2, the small quantum cohomology. This is the same story. So the story is that if you have, this is just the higher genus version of that. What did we do there? We just said over there we had Hilbert of C2, and we were mapping for a small quantum cohomology. You're just mapping a genus 0 curve, rational curve, and nothing else, right? We're mapping the P1 into here. By the functoriality property of the Hilbert scheme, this gives you a flat family over P1 of zero-dimensional subschemes of C2. These are zero-dimensional for every point of P1, right? Every point of P1 gives you some finite subscheme. So this is something like that. So if you have some finite cover of P1, so this is your P1. In some sense, the image of P1 inside here can be realized as some n-to-1 cover of P1, right? And then the correspondence with this, with the C2 times P1 Gromov-Witten theory was that, okay, so now we know that we have some cover of P1 and we need to distribute n points on this cover. So we had this thing, and then for each marking on the P1, we had a factor of C2. We had divisors on C2. So we drew these divisors like that. And then we said that, well, inside here we are looking at Hilbert scheme of n points on C2, and I'm supposed to basically give certain relative profile to this, how this curve meets this guy. So we basically said maybe it meets in some fat point, maybe it meets in some isolated point. So we had these partitions. So on each one of these divisors, of course this was genus 0 with 3 mark points, because that's what is the quantum cohomology. So we had another one also here. So we had more profiles, mu1, mu2, mu1, mu2, mu3, and so on and so forth. The sum of the cardinalities of these ones always is n, but then they could have different ways of clustering the same number n, and those are basically, we partition n in terms of labeling them by cohomology classes on C2. So we have some cycle on C2, and we say on this cycle I put in n1 many points, and on some other cycle, maybe a divisor, I put n2 many points, such that n1 plus n2 is equal to n. So if you look at this picture, you can basically see that in the small quantum cohomology in here is realized by certain Gromov-Witten theory of maps to this threefold with certain relative condition along these divisors. This is exactly the same thing, except now we are doing it for every point of this moduli space. We have a moduli space of stable maps to this threefold. This is a higher genus curve now with this relative condition. We do exactly the same thing. So that's why if I want to match cohomological field theories, I need to match two cohomological field theories associated to Gromov-Witten theories, equivariant Gromov-Witten theories. Here our target is this space. Okay, except one thing, that this is an orbifold Gromov-Witten theory for now, and this space right now is in here. Okay, so that's all I wanted to say. So then, okay, so the moduli space m dot h pi mu 1 to mu r has pi relative virtual dimension minus n times 2g minus 2 plus r plus sum from 1 to r of length of these partitions mu I. That's the expected dimension of this stable maps moduli space. Pi relative again means for every point of this moduli space m bar gr, as soon as you fix the genus and you tell me what is the number of marked points, my moduli space has this dimension. Stable maps moduli space has this dimension. Okay. The cohomological field theory, lambda bar, is defined as, I'm not going to actually give you any detail of the proof. I just want to define things so that you know where to look for it if you later want to study this problem. Define it, and then I just make a final statement. And then the similar thing for the stable pair moduli space, define it, and then what's the final statement? Because it's very detailed. And so lambda tilde gr of mu1 mu r, even though I have written the proof, but I don't think there is any point to go through the gory detail. But it is in their paper anyway. So u of b factorial epsilon lower star of m dot h times b of pi mu1 mu r virtual. That is what the definition of this cohomological field theory is. B is defined as branch point number. Branch point number defined by, it satisfies an equation. So 2h of b minus 2 is equal to b plus n times 2g minus 2 plus r minus I from 1 to r length of mu I. It satisfies an equation like this. If h times b is not an integer, then this thing vanishes. Okay. If HB, this guy, is not equal to is not an integer, then basically the moduli space of a stable mass becomes empty. H is the genus of your curve. So, okay. So what is the final statement I want to say? So final. Okay. What are the summary of statements? Summary of statements. First of all, it can be shown lambda tilde satisfies axioms of cohomological field theory. The three axioms of cohomological field theory. Second thing is, it can be shown lambda tilde satisfies some sort of differential equation, which is it's actually the divisor equation. It satisfies the divisor equation. Remember that for cohomological field theory of Hilbert of C2, divisor equation helps us to compute the R matrix for higher genus in terms of the lower genus R matrix. So this is also satisfies that. So satisfies lambda tilde of GR plus 1. This is the divisor equation. Mu R times this divisor is equal to ddu of lambda tilde gr of mu1 mu r. This is the divisor equation, so satisfies divisor equation. You need to show this thing, and it's very involved. Okay. And this uses degeneration technique as well, and so on. So, okay. Then, third thing is, they show that using these two, they show that which is the equivalence. So they show that the cohomological field theory, omega tilde, obtained from orbifold Gromov-Witten theory of sim n of C2 and cohomological field theory lambda tilde, which is orbifold Gromov-Witten theory of the threefold. Oh, I mean, basically not orbifold, but just the Gromov-Witten theory of this particular threefold that we constructed, and lambda tilde are equal in genus 0. In genus 0, and hence both semi-simple as cohomological field theories. So then the two cohomological field theories satisfy divisor equation, and the equality after restriction to equal to 0. So in fact, you can see that omega GR mu1 mu r restricted to u equal to 0 is the same as lambda GR mu1 mu r restricted to u equal to 0. For all bigger genus bigger than 0. And basically, this part actually follows from matching the moduli spaces and basically matching the obstruction theories of the two moduli spaces. Okay? And then using the property of the R matrix, now we know that the boundary conditions match, and then we can flow and obtain the higher genus R matrix. So basically, this is the statement. At u equal to 0, this is the higher genus one, and this is the higher genus one, and they both match. This u in here is the same as analog of in the Hilbert scheme case, is the analog of the thing that keeps track of the degree of the map. The degree of the map from the higher genus G curve with R mark points into the ambient space. So these are the constant maps. Okay, so then very similarly, you can, for matching the dt, for the dt part, for dt, you construct some lambda gr without a tilde in here, and you can show that it matches with the omega gr. So this is the sim n of C2. This is Hilbert of C2. And you can show that these two guys match. Okay? The only thing that you need to do in here, instead of this guy for us was the basically cohomological field theory associated to grammar within theory of the pi relative stable maps. In here, it will be a stable pair moduli space. Certain sheaf with one-dimensional support, which is a higher genus curve, together with its section. And finally, this is the theorem we discussed before, which is final theorem. This is again due to Pandri and Schenk, which is for all G bigger than equal to 0 and mu1 to mu r partitions of this n, they show that mu1 to mu r Hilbert of C2 matches with minus I to the I from 1 to R L of mu I minus cardinality of mu I mu1 to mu R sim n of C2 genus G after variable change. Minus q equal to e to the I. So a segment of their paper is invested on proving this statement, since it's extremely crucial. Okay, and then there is explicit calculations of what these R matrices are. So when they want to match cohomological field theories, really they explicitly calculate the R matrices of those cohomological field theories. And that's what we will do too in cases we want to calculate something new. Okay, yeah, I think it is roughly I can say, even though we didn't go to the gory details, because this is really actually difficult and complicated. But I hope that I just gave you a review of the recent progress on this thing. Yeah.
Question is, this is saying that there's some sort of relationship between quantum cohomology, C2, and its resolution.
Yes.
And this, I'm just a little bit puzzled that this condition is transcendental. Like the change of variable is transcendental. And in general, this of course doesn't hold.
No.
You resolve it.
No. So it is not simple. It's not easy to go from some kind of a stachygraph within theory or an orbifold grammar within theory to the resolution. So, for instance, there's some notion of quantum Krapent resolution, or quantum Mackay correspondence, basically, that tells you quantum cohomology of the singular thing downstairs is kind of related to the one upstairs via some. I mean, this is in that thing. So, for instance, there are, even in mirror symmetry, there's a lot of work done on this. So, for instance, you have a variety. Okay, an example of this. This is a hard way of explaining it, but to give you an insight, there are examples where you start from a variety, and you go to the mirror of that variety, and you look at the complex structure moduli space of that variety. That's the P1, and every P1 comes with 3 distinguished points. This one too. And the 3 distinguished points are the conifold point, the orbifold point, and the large volume point. The 1, which is the diagonal equator of the P1. Then there is some function that the story actually started with string theorists realizing that on the mirror there is a function that you can describe everywhere on that complex structure moduli. And this, they call it topological string amplitude.
Sorry, see?
Topological string amplitude. Topological string amplitude.
Oh, okay. Yeah.
And when you restrict the topological string amplitude to neighborhoods around these 3 distinguished points of P1, then you can describe it in certain flat coordinates around those. And so basically, let's call it something like an f, and it's a function of holomorphic and anti-holomorphic variables.
Sure.
And then you can take the topological limit of this thing, or anti-holomorphic limit of this thing, maybe this thing going to infinity or something, and you will get this holomorphic function. And the conjecture was that, and it still is, that it gives you the potential, the Gromov-Witten potential of the original variety. You see, so something on the moduli space of complex structures of the mirror captures something about the original variety.
Okay. Yes.
Now, how is this related to here? Is that you have these 2 points, orbifold point and the conifold, for instance, for the variety. One of them is literally the Krapent resolution of the other.
Oh.
Your function, though, is universally defined everywhere on this P1. Your function doesn't change. So you restrict your function to the 2 points. One of them is a singular variety or a static thing, and the other orbifold. The other one is just a resolution of that. And when you take the topological limit, you realize that the same function actually gives you the Gromov-Witten potential of this variety versus the other variety.
Yes.
So this identification was expected actually from the string theory point of view. They were saying, so okay, I have some universal function which after taking the limit around 2 points of this P1 give me 2 different things. So can we see if on the algebraic side, on the variety itself, is there any connection between quantum cohomology of the resolution versus the orbifold, the quantum cohomology of the singular guy? And that actually was investigated If you search on these papers of the quantum Mackay correspondence and things like that, that was investigated before. So here is somehow a version of that, because one of them is the resolution of the other, and it's very involved how to prove that this partition function matches with the other higher genus partition function. But I'm just telling you where to look for it. I mean, yeah. Any other questions? Okay, so thank you for coming, and it was great. We did it. Yes. All right. Cheers.